Friends, hope you are doing well. Last class we discussed some multiplexing elements, and prior to that we studied some of the ADCs and DACs. Today we'll discuss uh, data acquisition system. Remember the signals those we'll be getting from our mechatronics systems, like I have a processor or a sugar processing plant, let us say. And in that sugar processing plant, I have got boilers, I have got mixers, I have got reactors, I have got filters. And from each of these units, I'll be getting data from the sensors. Now, this data from the sensors is needed to be processed, and it is to be processed by a computer, let us say. So we need to make this analog data from the sensors suitable for the computer to receive, or the microprocessor to receive, and thereafter it will send the control signals to maybe the actuators, or it may send the control signals to our controlling devices. So data acquisition system plays a very vital role in mechatronic systems. As you can see in the block diagram, I have got many analog inputs. These correspond to various sensors. Various sensors will be sending, maybe pressure sensor will be sending some analog data. Then temperature sensor will be sending some analog data. Maybe the flow sensor will be sending some analog data. Like that, mass flow rate, and whatever are the parameters, different sensors will be sending different data. Now, as we discussed in the last class, the multiplexer, what way it helps? The multiplexers processes the signal one by one. Okay, so it doesn't process the signal simultaneously. In that case, I'll be requiring different ADCs, I'll be requiring different amplifiers, but I'll be using these ADCs or DACs and whatever are the components. Only single component is sufficient, because multiplexer, what it does is it receives the sensor data one after the other, and this sensor data, which is analog signal, that will be amplified, and it will be sent to the A to D converter, analog to digital converter. Now this analog to digital converter modifies or converts that analog amplified data into digital data. Now this digital data is either sent to the control elements or control register or the status register, or it is sent after processing, it is sent to the data register. And thereafter, if there is a control requirement, the controller part of the processor will take that data from the data register, and process it and send to the controller. Or this data, when we are sitting on a computer terminal, now this data acquisition card will be there put inside our motherboard. So there will be one slot for receiving for this data acquisition card, the data acquisition. So this is called as a DAQ card or data acquisition card. So this is the connector for that data acquisition card. So from my computer, I'll be connecting the connector to this data acquisition card. So as and when from my computer screen, I'll be asking for maybe temperature data. So this temperature data, this connector will send a signal to the data register. So the data register will give the required data to the computer, back to the computer. And then on the computer, you can either manually process, or the computer as a controller will make a decision of its own what to do with that signal. So this is how this data acquisition system plays a very important role in mechatronic devices. So let us see, the term data acquisition for RDAQ is used for the process of taking signals from sensors and inputting that data into a computer for processing. The sensors are connected generally via some signal conditioning to a data acquisition board. So sensors are connected through a signal condition. What are these? These are the signal conditioning devices. Those are not directly given to the computer. So multiplexing, amplification, and ADCs or DACs as the case may be. So the sensors are connected generally via some signal conditioning devices to a data acquisition board which is plugged into the back of the computer. As I said, on the motherboard of the computer, we have this data input slot. In that slot, this DAQ card or data acquisition card is just inserted, and thereafter that data is taken for further processing. The DAQ board is a printed circuit board for analog inputs. Basically, it provides a multiplexer, an amplifier, analog to digital converter, then registers for storage of data, and then control circuitry so that sampled digital signals are applied to the computer system. The computer software is used to control the acquisition of data via the DAQ board. The computer, when the program requires an input from a particular sensor, it activates the board by sending a control word. See, listen to me very carefully. When the program requires an input from a particular sensor, it activates the board by sending a control word to the control and status register. The data register stores this data, and as per requirement, this data is shared with the computer. The specifications for a DAQ board include the sampling rate for analog inputs, which might be 100 kilo samples per second. So 1 lakh samples per second it can receive. So at such a faster rate, the DAQ board can receive the data. So this is how my DAQ works. Let us go further. Up till now, for the last few lectures, we have seen analog signal conditioning. We'll see some of the aspects of digital signal processing. Now, digital signal processing or discrete time signal processing is the processing of the signal by a microprocessor. Earlier in analog signal conditioning, your amplifiers, filters, ADCs were doing the signal conditioning work. Comparators were used for signal conditioning. Now, in case of digital systems, the microprocessor does all the work. Let it be comparison, let it be amplification, let it be conversion. So whatever are your requirements, your microprocessor does all these signal processing work. The digital signals are discrete time signals. They are not continuous functions of time, but they exist only at discrete times. The analog signal conditioning requires components such as amplifiers and filter circuits. Digital signal conditioning can be carried out by a program applied to a microprocessor. To change the characteristics of a filter used with analog signals, it is necessary to change hardware components. In case of analog signal conditioning, we needed to make some changes in the hardware components, whereas in the digital signal conditioning, the characteristics of a digital filter can be changed through the program of instructions given to a microprocessor. So this is the benefit of digital signal conditioning. Microprocessor, through programs, we can control each of these functions. Let it be comparison work, let it be filtering work, let it be conversion work. Just through a program given to a microprocessor, I can alter the requirements, or I can work as per my requirement. Whereas in analog signal conditioning, we needed to change the hardware components. With a digital signal processing system, there is an input of a binary word representing the size of a pulse. So with a digital signal processing system, there is an input of a binary word representing the size of a pulse, and an output is another binary word. So in digital signal processing, input is a binary word and output is also binary word. The output pulse at a particular instant is computed. The output pulse at a particular instant is computed by the system as a result of processing the present input pulse together with previous pulse inputs. So as per the availability of pulse data, I can process that digital signal. Let us see a few of the fundamentals of digital signal processing. The digital logic, we are not going into the details of all the logic functions, but we'll just have an overview. Two types of logics we'll be considering here. There is a combinational logic and the second is sequential logic. So what is the basic difference? Combinational logic, uh, if you remember in second year, you must have studied some of the logic gates. We'll just revise those gates. So these are the conditional requirements. If A is equal to B, then C should be like this. So these conditional requirements, when they are there, we use combinational logic. Remember, in combinational logic, we don't have any memory component as such. Whereas in sequential logic, we have memory components involved. And in sequential logic, basically, if you consider some mechanical application of a sequential logic, let us say I have a power press which is electropneumatically actuated. So I can put conditions where, unless and until the job is fixed in the fixture, uh, the working button of the press should not operate. So these conditions I put. So unless and until that switch, whatever limit switch I have placed there, or whatever sensor I have placed there, which is showing me about the closure of the fixture where the component is fixed, unless and until that switch is enabled, the further circuitry will not work. So such and such logical requirements when are there, and when there is one memory requirement as such, we going for sequential logic circuitry. Now first we'll see the combinational logic aspects. Many control systems are concerned with setting events in motion or stopping them when certain conditions are met. So wherever there are conditional requirements, as I said, if I want to have, if A and B and C, if these conditions are fulfilled, then only D should operate. So certain conditions are there in our day-to-day mechatronic system applications. We go in for combinational logic circuitry. For example, with the domestic washing machine, the heater is only switched on when there is water in the drum. So this is one condition we are considering here, and it is to the prescribed level. Whether the water is at the prescribed level, then only the heater should be put on. Such control involves digital signals where there are only two possible signal levels. So uh, either on, off, high, low, or enable or disable. So only two conditions, on or off, enabled or disabled, high or low. So digital circuitry is the basis of digital computers and microprocessor based control systems. Let us quickly see. There are two input signals which are either yes or no signals, and an output signal which is a yes or no signal. So binary signal, as we said, yes or no, or 1 or 0, enable, disable, 1 or 0. So like that, input is also binary, output is also binary. The controller is here programmed to only give a yes output if both the input signals are yes. That is, if input A and input B are both 1, then there is an input of 1. Such an operation is said to be controlled by a logic gate. This is an example of AND gate. We'll see the details later on. There are many machines and processes which are controlled in this way. The term combinational logic is used for the combination of two or more basic logic gates to form a required function. So this is what is combinational logic. Let us quickly see few of the gates. Let us be attentive, friends. As I said, I have taken all these things from a book by Bolton. Remember. So AND gate, please be attentive. First figure corresponds to representation in the form of switches, so that we can easily understand. So these are the convention of US symbols, and this is the universally accepted or international symbolic representation. So these two are useful. In fact, this is the most accepted symbolic notification of AND gate. So, so what is the logic equation? A dot B is equal to Q. So A and B are the inputs, and Q is the output. Please be attentive. So let us understand. If condition A is fulfilled and B is also fulfilled, then only there will be some output. So if the switch A is on and B is on and B is on, then only there will be output Q. If A is on and B is not, B is off, output will not be there, right? So this is the symbolic representation. A, B, and gate, representation of AND gate, and the output is Q is equal to A dot B. See what are the four conditions. Please be attentive. A is off, that is 0. B is 0, output Q will be 0. If A is 0, that is A is off and B is on, because this is AND gate, output still will be 0. Now A is on, that is A switch is closed, and B is off, B is open, still the output is 0. And then if A is on, B is on, that is A is 1, B is 1, then the output is 1. A is high, B is high, output is also high. A is enabled, B is enabled, A and B is enabled, then only output Q is enabled. This is what is called as truth table for AND gate. It is very simple. Please, you can refer it once again so that you can understand. This is the AND gate. Let us see the OR gate, right? So same switching arrangement, and then your international symbolic representation. Greater than or equal to 1 is the symbolic representation of OR gate. A and B are input and Q is the output. And the equation is A plus B is equal to Q. Now let us see the truth table now. If A is 0, so A is off and B is off. We are talking about OR gate. So either A or B will do. So if A is off and B is off, so Q, output Q will be 0 or off only. If A is 0, that is A is off and B is on, B is switched on. So this is OR gate. A or B, any one of it is on, then I'll be getting output as on or 1. A or B, 0. A is 0, but B is 1. So either of the two, A or B is 1, then output Q will be 1. See the third condition. A is 1, so A is put on. B is put off, it is switch off. So A or B is 1. So A is 1, fine. B is 0, no problem. Either A, if it is A is 1, even though B is 0, I'll be getting 1. Then if finally, if A is on and B is on, A or B is on, A or B is on, then Q will be on. So this is the truth table for OR gate. I think friends, we'll stop for today. Let